So, we continue in this lecture our discussion of mean field models. Today, we will talk about the deformed shell model. Now, as nucleons are added beyond, let's say, a closed shell, initially, at least due to the residual attractive interaction. So, the mean field takes care of the average behavior of a nucleon and nucleus. But if I add particles, then this odd particle or particles, they interact with the nucleus, and they interact in a way which is not really taken care of by the average field. And so, there is a so-called quote unquote residual interaction, and this is of an attractive nature. So, the nucleons which follow this odd nucleon actually contribute to an overall small oblate deformation. As the number of nucleons you add becomes more and more, then this nucleus becomes actually prolate. And the mean field now can be thought of as being deformed. That is a better description. You can still think of it as in terms of a single or particles moving in a spherical mean field. And of course, what will happen is that this description will become more and more complicated. It will have, if you do, perturbation theory, you will get components which are huge in number. So, it becomes more economical to change the mean field itself and think of it as being a deformed mean field, and then calculate the single particle energies of particles in that mean field. There is a price to pay for that the single particle angular momentum is not conserved, only its projection along the symmetry axis is confirmed. Why do I say symmetry axis? Because the kind of deformations that we get are usually of the quadrupole type, and there is a symmetry axis corresponding to this quadrupole deformation. Now, this approach was of course put forth by Bohr and Mortensen, but the actual calculation of single particles in a deformed mean field was done by Nielsen. Now, such a description can also be gainfully employed in the context of a rotating mean field. So, if you have a deformed nucleus and then that is rotating fairly rapidly, then you think of the average angular frequency with which it is rotating, and then you can calculate again the single particle energies in this rotating mean field. So, it is the same approach that we adopted for an average deformation of the mean field. So, now let us go back and say what is the evidence for deformation in nuclei. Now, suppose you consider the low-lying spectrum of a spherical nucleus, quote unquote spherical, because of course it can there can be quantile fluctuations which take it to other deformations, but at least the average shape of the nucleus is a sphere, and this is so, for example, for 144 samarium. You will notice that the proton number is 62, but the neutron number is magic at 82. Okay. So, this nucleus exhibits a first excited state which is rather high, it is at 1.66 MeV, and then there is a bunching of states. So, there is a 3 minus at 1.8, 4 plus at 2.19, 2 plus, another 0 plus, all around about 2.4 MeV plus minus 0.4 MeV, or let us say 2.5 plus minus 0.4 MeV. Okay. So, in fact, it turns out that these are good, so-called good vibrational nuclei. Okay. So, even a spherical nucleus can vibrate, and then that sort of collective excitation leads to this kind of spectrum. The 3 minus state is of course a kind of is different from this quadrupole vibration. It is actually an octupole vibration. So, it corresponds to a state which has used the octupole degree of freedom. And in any case, you can see that there is a big gap between the ground state and the first excited state. On the other hand, if you put more and more neutrons in this nucleus, in fact 8 more neutrons in this nucleus, then you actually see the spectrum drastically changes. From a big gap like this at 1.66, you go to a low-lying 2 plus state which is just 122 keV, and then you observe a nice rotational band. So, if you were to plot these energies as a function of j into j plus 1, you get a more or less a straight line fit. Okay. So, this is a typical rotational band of a deformed nucleus. Similarly, if you do Coulomb excitation, so if you shoot let us say a lead projectile onto a plutonium target, and what is shown here is the Coulomb excitation spectrum for 242 and 244 plutonium using the lead nucleus which is bombarding it just around the Coulomb barrier. Actually, it is better to stay a little below the Coulomb barrier, so that you can calculate these things well, because then you have a Coulomb potential whose effect on lead-208 you can compute pretty accurately, and the small nuclear interaction is only a very tiny correction to this potential. So, in any case, you see these energies, they are it starts out with 45 keV as the first excited state, 147 keV, 306. So, the lead as it comes by this plutonium nucleus, it excites various states, and it stays long enough that it can excite from 2 plus to 4 plus, 6 plus and so on, and you can populate states up to about 26 units of angular momentum. And this is so for both of these nuclei, both of which are deformed, and you can see the spectrum. In 244, the spectrum extends up to about 24 or so, whereas here it extends up to about 26 or so. So, what happens is that in this heavy nucleus, if you go higher and higher in angular momentum, ultimately the nucleus tends to fission, and so that is where that limits the maximum angular momentum that you can excite. Where this not to fission, you might have excited a few more angular momentum states. Okay. So, these nuclei also show a very nice rotational kind of spectrum, and this is quite uncharacteristic of a spherical nucleus. A spherical nucleus is a very different kind of spectrum. Okay. So, the other observable is that there are quadrupole deformations of nuclei, both in the ground state and in, of course, the excited state. So, here what is plotted is the distortion parameter, or the actually it is the quadrupole deformation parameter, which is defined here. The delta is in terms of the radius along the symmetry axis by minus the radius squared in the perpendicular axis, and divided by R3 squared plus 2 R perpendicular squared, because if you have a prolate nucleus, it is elongated along, let us say, the z axis, but is shorter in the x and y axis. Of course, it is symmetric. So, it is symmetric with respect to rotation along the z axis. Okay. So, it is like a cigar. So, you can define a quantity delta like this. You can also compute a quantity of delta r, which is R3 minus R perpendicular, and you can also calculate the average R. That turns out to be 1/3 of R3 plus 2 R perpendicular. In any case, the distortion parameter, which is related to the deformation parameter, the quadrupole deformation parameter, varies right from about 0.335 to about 0.15 as you move from samarium isotopes to osmium, and then radium all the way up to californium. So, it again rises. So, we saw plutonium, the excitation spectrum corresponding to a rotational band in plutonium, but you can see similar things in other nuclei. In fact, these quadrupole moments are also measured using atomic spectroscopy. Okay. So, there are various ways of measuring these quadrupole movements, and you can infer them from the rotational low-lying rotational bands, but also from other atomic physics measurements. So, in any case, this is another evidence that there is quadrupole deformation in the rare earth and actinides. Similarly, there is something called the reduced electromagnetic transition matrix element. This is the Be2. We will come to that in the subsequent lecture. The reduced transition matrix element, the Be2 for instance, as if you compare it to the single particle Be2, then it is enhanced in this rare earth and in the actinide region, and by a couple of orders of magnitude. For instance, this is of the order of about 200 or so. In the case of the heavy actinides, it even goes up to about 350 or so. Of course, since this is also proportional to the number of protons that are there that are contributing to this deformation, even if nuclei are deformed in light nuclei, their Be2 is smaller. Okay. So anyway, so these are the kind of evidences, experimental evidences that we have for going over to a deformed mean field, deformed shell model, and that's also sometimes called the Nielsen model. So what you do is you break spherical symmetry of the mean field. You have an anisotropy of the mean field, and that you can do it in various ways. For instance, you can you can demand axial symmetry, which is probably so for many nuclei in this rare earth and actinide region. And then you can orient the nucleus in an intrinsic frame, so to speak. So if this nucleus and the mean field has an axis of symmetry with respect to rotations, of course, around that axis, usually we denote it by the z axis, then the mean field is a function of r and theta. Okay. So you have v equal to v0, which is just dependent on r, plus a v2 term, which is proportional to the Legendre polynomial of second order, which is of course related to cos theta, where theta is the polar angle of the single particle with respect to the symmetry axis. And so the r of theta is given by r0, which is a sort of average radius of this deformed nucleus, plus into 1 plus 2/3 of delta, we had defined delta earlier, and times P2 cos theta. So the Rx and Ry are the same for a prolate nucleus, and this is just given by R0 into 1 minus delta by 2. Rz is given by R0, 1 plus delta. Of course, if you have oblate deformation, then this delta would be negative, and again you have x and y the same, but Rz is smaller. Delta has a negative sign, then it subtracts, and then you have Rz which is smaller than Rx and Ry. So this is done so as to maintain to first order the volume of this ellipsoid is the same as the parent sphere. So you just take a parent sphere and then deform it such that you get a cigar shape or a flattish idli shape nucleus. Another parameterization of the radius parameter with respect to quadrupole for quadrupole deformations is r is equal to r0 plus 1 plus alpha mu y true mu. This is the spherical harmonic of order 2, which depends on theta and phi. These 5 alpha mu's are expressed in terms of 3 Euler angles, and beta the quadrupole deformation, and gamma, which is the triaxiality parameter. So the L equal to 1 term here, so y1 term is dropped because of course that corresponds to just a center of mass displacement, and that can be set to 0. For axial symmetry and reflection symmetry about a central plane, so then the number of parameters reduces. So what happens is that the alpha 0 is just beta times cos gamma, but alpha 2 is the same as alpha minus 2 because of this axial and reflection symmetry, and that's beta sine times gamma. So you can calculate the change in radius along the z direction to be a constant here times r0 times beta cos gamma, and delta Rx is the same thing in terms of cosine of gamma minus 2 pi by 3, Ry in terms of cosine gamma minus 4 pi by 3. Okay. Now, if gamma is equal to pi by 3, then of course, we call it a prolate oblate nucleus. If gamma is 0, we call it a prolate nucleus. And if gamma is somewhere in between, then you call it a triaxial nucleus, because then you have the x and y axis, the radii corresponding to that, they are different. Okay. This is a picture taken from a reference given here, and you can see that this is for a prolate nucleus, and this is the symmetry axis. So, if you rotate along the symmetry axis, uh, you have symmetry, and you have a single particle momentum j, and you have a rotational angular momentum r, and then you combine these and you get a total angular momentum, and the projection of these along the symmetry axis. So, for instance, the projection of the sorry, this is not the single particle j, this is the yeah, okay, this is the total single particle j. This is the individual, let us say, angular momentum of the particle. So, the projections of that are omega, and then the total projection of the total angular momentum along the symmetry axis is k. So, this just shows the kind of projections that you have of the various components of the angular momentum. You have a single particle degree of freedom, and you have a collective rotational degree of freedom. Now, what are the kind of shapes that this can take? How do they look like? So, for instance, you start out with a spherical shape, but there are nuclei which are prolate, and so this is along the z axis. So, you have a elongation along the z axis and symmetry along the x and y axis, the smaller radii along the x and y axis. And if you take a end view, so you look at it from this side, then of course you have this kind of projection that you get. Suppose you have a oblate nucleus, then of course it's a sphere which is pressed on top and bottom, and of course this is symmetric around the z axis still, but you have two x and y axes which are equivalent, and a z axis which is I mean, the deformation along the z axis is different from that along the x and y axis. So, these are the kind of deformations you have for lambda equal to 2, lambda equal to 3. So, this is the quadrupole deformation, this is the octupole deformation, this is the hexadecapole, and so on. And you can of course have a spherical nucleus, but you can have vibrations of the lambda equal to 2 type or lambda equal to 3 type. Okay. Alternately, if you consider quadrupole deformation, then you can have beta vibrations, you can have gamma vibrations as well. Okay. Because in the case of quadrupole, those are the two parameters that you have. Okay. So, the Hamiltonian now, if you continue with a harmonic oscillator and its extension, then you have a harmonic oscillator potential which we started out with for the spherical case, which only depends on r. But now, because of this because of the quadrupole deformation, you have to add a small term which is proportional to delta, which is proportional to the quadrupole deformation, and a p2 cos theta. Equivalently, in Cartesian coordinates, you can write this down as half m omega z squared plus omega perpendicular squared, because you said that is the same whether it is in the x or y direction. So, there is a symmetry with respect to rotation around the z axis. And it turns out that if you want to again conserve the volume of this sphere, then you get omega z squared is equal to omega 0 squared times 1 minus 4 by 3 delta, and omega perpendicular squared is 1 plus 2/3 of delta. So, omega squared is equal to 1/3 of the average of the square of omega x, omega y, and omega z squared, and this is just 1/3 of 2 omega perpendicular squared plus 2 omega z squared. Okay. So, of course, you can notice that this term here omega z squared is like omega squared 1 minus 4 by 3 delta. So, since the nucleus is extended in the z direction, the corresponding oscillator frequency is smaller and it's larger in the case of the x and y directions. Okay. For small deformations, one can use perturbation theory, and the energy perturbation delta E, which has the quantum number associated with it, which is the n, which is the overall radial quantum number, L is the single particle orbital angular momentum, J is the single particle angular momentum, which is decided by the orbital and spin angular momenta, and m is the projection of that angular momentum along the z axis. So, this is given by 2/3 h cross omega 0 times delta. So, it is proportional to the quadrupole deformation parameter. So, you can see that if delta goes to 0, then this term vanishes, and n plus 3 by 2, this is of course, this is the same term that we had earlier for the spherical nucleus, and then a term 3 omega squared minus j into j plus 1. Omega is just the projection of the single particle angular momentum along the symmetry axis. So, the single particle angular momentum j, total angular momentum j, its projection on the symmetry axis, this is what is omega. Okay. So, this is 3 omega squared minus j into j plus 1 divided by 4 j plus 1. So, for small delta, of course, greater than 0, then this correction is negative. So, delta E is greater than 0 for large omega. Okay. For small delta, but it is negative, then delta E is negative for large omega. Delta E is 0 for small omega. Okay. So, it is just the reverse. So, for a prolate deformation, this is delta E is 0, less than 0 for small omega, greater than 0 for large omega. On the other hand, for oblate deformation, delta E is less than 0 for large omega, but greater than 0 for small omega. So, the behavior reverses. We will see that in the so-called Nielsen diagram, where you plot the single particle energies as a function of delta or beta 2, whatever case may be. For large delta, the single particle energy is of course given by n3 plus half h cross omega 0 plus n12 h cross omega 0, n1 plus 2 plus 1 h cross omega 0. Since the mean field breaks the spherical symmetry of the mean field, we have already said that the angular momentum j is not conserved, but the projections of L and j are conserved and they can be used to label the states. The total angular momentum of course is conserved. That is just the single particle angular momentum plus the rotational angular momentum. This is conserved. So, individually R and J are not conserved, the total angular momentum is conserved. Okay. So, this is how the single particle energies behave in a deformed nuclear potential. So, this is plotted, these energies are scaled by some quantity here and plotted as a function of this delta oscillator parameter. So, if it is positive, for instance, if delta is positive, then the low k values or low omega values are smaller and the high omega values are larger, as you can see here. So, this is the omega value, or it is also sometimes called the k value, and you can see that for instance, take this f7 half, then the half is lowest for the prolate shape, and this is 3 half and this is 5 half. Okay. On the other hand, for the f7 half, the f for the delta which is negative, then 7 half is the lowest, 7 half, 5 half and so on. Okay. 3 half and half, you have 4 states. So, this is in general how the splitting occurs. So, whereas all of them were degenerate at for the spherical case, the degeneracy is lifted as deformation increase and the split becomes larger and larger. Okay. Now, for an axially deformed even nucleus, the rotational spectrum, it turns out, is given by this h cross squared into j plus 1 into divided by 2 a moment of inertia parameter plus the starting energy E of k. So, here the j pi is equal to 0 plus, 2 plus, 4 plus for a k pi equal to 0 plus band, and the j pi is equal to k plus 1, k plus 2 for a k not equal to 0. This actually happens because of the symmetries involved in the nucleus, and the j is the so called moment of inertia parameter. The rigid body value, of course, we know, we can compute that from just doing an integral, and it turns out to be 2/5 of mr squared, where m is the mass of the nucleus and r is the uh, radius of the nucleus for a sharp cutoff. So, it's just a sphere of radius r. Uh, However, for and you can compute that the small correction that you have if you have a deformed nucleus, it turns out there is of the order of this times 1 plus about 0.3 beta 2. Uh, However, experimentally, the moment of inertia is found to be about 30% or 40% of the rigid body value, at least for the low lying states. Okay. So, this is the systematics of the moments of inertia. So, what is plotted here is the h cross 1 by h cross squared times I, where I is this moment of inertia parameter in MEV inverse as a function of A. You can see that for the rare earth isotopes, there is a systematics as you go from lighter to heavier nuclei, but all of them actually undershoot the rigid body value that you expect lies somewhere here. So, it is between, as I said, 0.3 to 0.4 of the rigid body value. Also, there is a small staggering between the odd Z, odd N and even nuclei, their moment of inertias. Okay. So, the intrinsic quadrupole moment is defined like this: Q0 is equal to 3z squared minus r squared rho of r, where rho of r is the charge distribution, and this is 4 by 3 times the delta that we saw uh, summed over all the Ri squared of all the particles. So, the observed quadrupole moment is of course Q0 observed in the lab 3k squared, where k is of course the projection of the angular momentum, total angular momentum along the z axis, minus j into j plus 1 divided by product of j plus 1 and 2j plus 3. And we will come to this, the so called reduced transition probability from j to j minus 2 is given by some constant times the intrinsic quadrupole moment into a j into j minus 1 divided by 2j into 2j minus 1. Okay. This is just for completeness sake, this is how an oblate nucleus would look like with a which has a beta of 0.4, and this is how it will look like with a for a prolate nucleus beta 0.4. So, in any case, you can see that the BE2 is related to the intrinsic quadrupole moment. Okay. The single particle spectrum in a deformed nucleus, again this is the same thing, which is but plotted over uh, a larger deformation space, and you can see that there is, of course, we have seen this bunching of levels uh, in the spherical case. Uh, so, where the axis ratio is 1:1 along all directions, 1:1 to 1 actually. In the case of prolate deformation, where the long axis is a factor of 2 larger than the short axis, again you see bunching of levels. Okay. So, this is the so called, there appears to be a kind of quote unquote shell effect or shell closures at deformations which are not 0, but correspond to a long to short axis of 2:1, but also with a smaller shell effect, but it exists also at even higher deformations where the long axis to short axis is a ratio of 3:1. So, the 2:1 is called the so-called super deformed state, which I think we will see the example of that, and hyper deformation where this is 3:1. Similarly, if you were to plot the potential energy versus deformation for a nucleus, and this has been done in the so-called shell plus liquid drop calculations, then these in a classical nucleus you would expect this kind of behavior. The potential energy rises and then falls. Okay, and this, for instance, is useful in calculating, for instance, fission widths. So, if a nucleus is here, it has to tunnel through this deformation barrier and then it can fission. And if this barrier is of a smaller height, then you have more fission probability, and if this is higher or broader, then you have a smaller fission probability. However, it turns out that if you take into account these quantal effects, which are because of these single particle levels, in particular the shell effect at these deformations, it turns out that this is too simplistic, and a better calculation actually shows that you can have a deformed nucleus, a deformed minimum, but you can also have a super deformed minimum, albeit at a higher excitation energy. And then, of course, the average behavior is the same, that ultimately it goes over to two nuclei separating out, and that's for heavy nuclei, this corresponds to fission. But the point is that if you do a better calculation, you can have a minimum here, a so-called second well minimum at a larger deformation. And as we might see in some subsequent lecture, this has been actually observed. So, corresponding to the super deformation, where you have a long to short axis of 2:1, the first such case was seen in 152 dysprosium. Dysprosium 152 shows a pretty normal spectrum, say quote unquote normal. However, at higher excitation energies, it shows a so-called super deformed band, and this is manifested in the form of discrete lines with equal spacing, and the angular momentum inferred is as large as 60 units of h cross. Okay. So, this has a larger moment of inertia as well, and the BE2 is much larger than that for normal deformation nuclei. Normal deformed nuclei, we saw the BE2 was about 200 times single particle, whereas this is as much as 600 to 700 times single particle. So, this is a very large deformation, and this is the reference. So, this was done almost 40 years ago. The hyper deformed case, in fact, is still a work in progress. Nobody has yet found a hyper deformed evidence for a hyper deformed nucleus. So, people have been searching, and perhaps some of these big gamma tracking arrays might be able to find some such case in the periodic in the isotopic table. Okay, so in summary, we started with the evidence for static deformation, and we saw how gaps appear in the single particle spectrum in a deformed nucleus for quadrupole deformations of 0.3, 0.6, and then hyper deformed case of 0.9 as well. Okay, so I think I'll stop here. Thank you.